The velvet expanse of the night sky, a canvas ablaze with untold billions of stars, has always been humanity's ultimate frontier. For millennia, we have looked up, dreaming of interstellar voyages, of charting new constellations, of settling worlds beyond our sun's gentle embrace. We envision vast starships, arcs of civilization, traversing the cosmic dark with bold determination. But what if this grand narrative of endless cosmic expansion, this very foundation of our species' future, is a profound illusion? What if the majestic spiral arms of our own Milky Way, a breathtaking symbol of cosmic grandeur, are not a highway to the stars, but the very walls of an inescapable prison? This isn't science fiction speculation. This is the stark, quantifiable reality revealed by the deepest insights of modern physics, a truth that fundamentally redefines our place in the universe. We are bound, not by chains, but by the immutable architecture of space-time itself, anchored to a single star in a single galaxy, perhaps forever. Consider Proxima Centauri b, the nearest potentially habitable exoplanet, a mere 4 light-years away. To grasp this distance, even a signal travelling at the absolute speed limit of the universe would take over 4 years to reach it. Our fastest spacecraft, Voyager 1, would take roughly 70,000 years just to reach the nearest star system, let alone a potentially habitable world. The chasm between our boundless ambition and the universe's unyielding scale is not merely wide, it is an abyss of cosmic impossibility. In this episode, we embark on a sobering intellectual expedition to uncover the true reasons for our cosmic confinement. We will explore the mind-bending distances that mock our fastest ships, confront the unforgiving laws of physics that govern all motion, delve into the insidious effects of cosmic radiation on human biology and spacecraft integrity, and finally, face the terrifying psychological cost of eternal isolation in the cold, silent void. If this profound journey into the very limits of our cosmic reach intrigues you, if you seek to understand the universe not as we wish it to be, but as it truly is, then join us. Subscribe to Terran, hit the like button, and share this exploration into humanity's ultimate, undeniable boundaries. The allure of the cosmos, a tapestry woven with starlight, often obscures the chilling truth of its scale. When we speak of distances in space, our terrestrial measurements become meaningless. Kilometers, miles, even astronomical units. The average distance between the Earth and the Sun simply collapse into insignificance. To truly comprehend the vastness that traps us, we must recalibrate our minds to the light year, a unit that, despite its poetic sound, represents an almost unimaginable gulf. It is the distance light, the fastest entity in the known universe, travels in 1 Earth year, approximately 9.46 trillion kilometers. This single, blinding constant c forms the very bedrock of our cosmic prison walls, a speed limit woven into the very fabric of space-time itself. Our immediate cosmic neighbourhood offers the first, daunting taste of this reality. The nearest star system to our own, Alpha Centauri, is a staggering 4.37 light-years away. Within that system lies Proxima Centauri, a red dwarf orbited by Proxima Centauri b, the closest known exoplanet with the potential for liquid water, and therefore life. This tantalizing prospect, a mere whisper of habitability, is nonetheless an almost infinite journey. To truly put this into perspective, consider humanity's fastest emissary, the Voyager 1 probe. Launched in 1977, after nearly 5 decades of uninterrupted travel, it has barely scratched the surface of interstellar space, now a little over 24 billion kilometers from Earth. At its current velocity of approximately 17 kilometers per second, Voyager 1 would require over 73,000 years to reach Proxima Centauri. That is a span of time longer than the entirety of recorded human civilization, longer than the rise and fall of countless empires, all for a destination that is literally our closest stellar neighbour. This journey would require not just decades, but millennia, transforming any crew into a forgotten memory before arrival. Beyond Proxima Centauri, other nearby stars like Barnard's star, at about 6 light-years, and Sirius, the brightest star in our night sky, at 8.6 light-years, recede further into the astronomical distance. Each light year multiplies the travel time, transforming hypothetical journeys into multi-millennial expeditions. The European Space Agency's Gaia mission, an ambitious project launched in 2013, has meticulously mapped the positions, distances, and motions of nearly 2 billion stars within our galaxy. Its unparalleled precision in astrometry provides a chilling confirmation of the sheer emptiness between stars. Even in our relatively dense galactic arm, the average distance between stars remains profoundly vast, a cosmic ocean where islands of light are separated by unfathomable voids, each a perilous, resource-scarce crossing. This vastness, far from being an invitation, is a stark warning. But the true scale of our imprisonment only becomes apparent when we extend our gaze beyond our immediate stellar vicinity to the galaxy itself. The Milky Way, our home, is a colossal barred spiral galaxy, estimated to contain between 200 and 400 billion stars, stretching across a diameter of roughly 100,000 light-years. Imagine the light from a star on the far side of our galaxy taking 100,000 years to reach us, having begun its journey when our species was still evolving on the plains of Africa. To cross this enormous expanse from one edge of our own galaxy to the other would take even a hypothetical vessel travelling at 99% the speed of light hundreds of thousands of years from an external observer's perspective, representing an inconceivable duration for any biological crew. Even with the effects of relativistic time dilation, which would shorten the subjective experience of the journey for the travellers, the objective passage of time in the universe outside the spacecraft would render their home galaxy utterly transformed upon any return. Then we consider intergalactic distances, the true scale of cosmic isolation. Our nearest major galactic neighbour is Andromeda, another colossal spiral galaxy, currently hurtling towards us at 110 kilometers per second, destined for a majestic collision in about 4.5 billion years. Yet, even this cosmic dance partner is a staggering 2.5 million light-years away. For light to travel from Andromeda to Earth takes 2.5 million years, a duration that far exceeds the existence of the genus Homo. The photons reaching our eyes tonight from Andromeda began their journey when our early hominid ancestors were just beginning to craft rudimentary stone tools, an epoch of primordial wilderness on Earth. This means that any spacecraft we could theoretically launch, even one capable of near-light speed travel, would take millions of years to bridge this gap. Even for the travellers, time dilation might reduce their subjective journey to tens of thousands of years, but such an odyssey would still span more generations than all of recorded human history, rendering the original mission and its purpose utterly meaningless over such an immense temporal gulf. This immensity is not an anomaly, it is the universal standard. Beyond Andromeda lies the Triangulum Galaxy, the third largest in our local group, at a distance of 3 million light-years. Our local group itself, a small cluster of about 50 galaxies, is gravitationally bound, a rare cosmic oasis, but the distances even within this close-knit neighbourhood are immense. Further still, the Virgo supercluster, a titanic aggregation of galaxy clusters of which our local group is a minor member, is approximately 50 to 60 million light-years distant. Travelling to this nearby supercluster, even at 99.9% the speed of light, would mean an earthbound journey spanning 50 to 60 million years. To put that into perspective, 50 million years ago, the Earth was dominated by primitive mammals, and the dinosaurs were already a distant memory. The very landscape of life on our planet has been utterly transformed countless times in the temporal blink that would represent a single trip to the Virgo supercluster. Any such voyage would be an irreversible one-way ticket, leading to a destination that would have fundamentally changed beyond recognition during the course of the journey. The Hubble Space Telescope, a venerable eye on the cosmos, and more recently the James Webb Space Telescope, with its unparalleled infrared vision, have allowed us to peer back to galaxies that existed over 13 billion years ago when the universe was in its infancy. Yet, due to the accelerating expansion of space itself, a phenomenon driven by the mysterious force of dark energy, those galaxies are now over 30 billion light-years away and receding from us at speeds that effectively exceed the speed of light. This isn't about objects moving through space faster than light, but about space itself, stretching, carrying distant galaxies away from us like specks on an inflating balloon. This cosmic expansion means that many galaxies are already receding from us faster than we could ever hope to catch them, even if we could somehow achieve light speed. They have crossed a cosmic event horizon, a point of no return beyond which their light will never reach us. And we will never reach them. The light we now perceive from these ancient galaxies is merely a ghost, a remnant of a time when they were within reach. Their current reality is utterly inaccessible. The Sloan Digital Sky Survey, SDSS, a monumental effort to map millions of galaxies and quasars across a vast swathe of the universe, has meticulously charted this cosmic web of structures, revealing the true scale of this accelerating retreat. Its three-dimensional maps confirm that every galaxy beyond our local group is destined to eventually disappear beyond our observational horizon. Projections based on the SDSS data and other cosmological observations indicate that in a mere 100 billion years, any future civilization in the Milky Way would look out into a night sky devoid of other galaxies, seeing only the ghostly, merging remnants of our own local group floating in an endless dark void. This is not merely a question of technological advancement. It is a fundamental property of the universe itself, an inescapable design feature. The distances aren't just large, they are actively growing, continuously pushing the walls of our cosmic prison further and further apart, ensuring our permanent, profound isolation within our galactic island. This vastness, this unrelenting scale is the first and perhaps most absolute barrier to our dreams of interstellar and intergalactic escape, locking us irrevocably within our own galactic bounds. Our yearning for extraterrestrial contact, for the discovery of other civilizations, is inextricably tied to these distances. Even if another advanced civilization exists on Proxima Centauri b, the round-trip communication time would be over 8 years. Imagine trying to conduct a meaningful scientific or cultural exchange across such a gulf. A conversation would span a decade, a generation, even centuries for more distant targets. This temporal barrier, born from the immense spatial separation, ensures not just physical isolation, but informational and cultural solitude. The universe's vastness is not just empty space. It is a profound temporal disconnect, fragmenting any potential cosmic community into isolated pockets of awareness, each forever a distant, unreachably faint whisper to the others. The dream of a galactic empire, of a unified human civilization spanning star systems, shatters against this simple, brutal fact. The universe is too big, and light is too slow. The vast emptiness between stars, the unimaginable gulfs of light years, would be daunting enough on their own. But these are merely the spatial dimensions of our confinement. Overlaying this immense canvas is an even more fundamental, unyielding barrier, the cosmic speed limit, a principle woven into the very fabric of reality by Albert Einstein's theory of special relativity. This isn't a technological hurdle we might one day overcome. It is an absolute law of physics, an unbreakable seal on our cosmic aspirations. At the heart of special relativity, formulated in 1905, lies the startling assertion that the speed of light in a vacuum, approximately 209,792,458 meters per second, is constant for all observers, regardless of their motion. This seemingly innocuous statement has profound implications. For light to be a universal constant, something else must be variable: time and space themselves. As an object approaches the speed of light, two primary effects known as time dilation and length contraction begin to manifest. Time slows down for the moving object relative to a stationary observer, and its length contracts in the direction of motion. However, for any object possessing mass, the ultimate consequence of this cosmic speed limit is that it can never actually reach the speed of light. This impossibility is rooted in Einstein's most famous equation, E(mc)2. This elegant formula reveals the fundamental interchangeability of mass and energy. As an object accelerates, its kinetic energy increases. According to relativistic physics, this increase in energy is inextricably linked to an increase in its relativistic mass. The faster an object moves, the more massive it effectively becomes. To reach the speed of light, an object with any non-zero rest mass would require an infinite amount of kinetic energy, transforming into an object of infinite mass. This isn't just an impractical amount of energy, It's a literal infinity, a quantity that the universe simply does not possess and cannot provide. The speed of light is not a goal to be attained, but a threshold that massive objects can only approach asymptotically, forever tantalizingly out of reach. This isn't mere theoretical speculation. It's a phenomenon that has been empirically confirmed countless times in particle accelerators around the globe. At facilities like CERN's Large Hadron Collider, LHC, in Switzerland, protons are accelerated to astonishing velocities, reaching 99.991% the speed of light. These tiny particles, each possessing a minuscule rest mass, are pushed to energies equivalent to that of a flying mosquito. Yet, despite the immense power injected into the system, consuming enough electricity to power a small city, those final infinitesimal increments towards true light speed become exponentially harder, demanding ever-increasing, indeed ultimately infinite energy. Every fraction of a percent closer to C requires a disproportionately larger surge of power, starkly demonstrating the relentless, unforgiving mathematics of relativistic mass increase. If we cannot propel a single proton to light speed, the task of accelerating a colossal spacecraft, weighing thousands of tons and carrying an entire ecosystem of humans and their necessities, becomes an exercise in cosmic futility. To illustrate the sheer scale of this energy barrier, let's consider a hypothetical ARC spacecraft designed for interstellar travel, perhaps weighing a modest 10,000 tons. To accelerate this vessel to even 90% of the speed of light would demand an energy input equivalent to the total energy output of the entire Earth for hundreds, possibly thousands of years. Pushing it further to 99% light speed would require energy on the order of converting entire terrestrial planets into pure energy, a feat that is not only beyond our current capabilities but borders on the physically absurd. Even if such energy could be generated, the fundamental problem of how to store, contain, and then harness it for propulsion without instantly annihilating the spacecraft itself remains an intractable puzzle. Our current fusion reactors, still experimental, barely produce net energy for milliseconds. The gap between that and a star-scale energy source for relativistic propulsion is not merely quantitative but qualitative. Furthermore, the classic Tsiolkovsky rocket equation, a bedrock principle of rocketry, introduces another layer of impossibility. This equation dictates that to achieve high velocities, the mass of the propellant expelled must be many times greater than the mass of the payload. For relativistic speeds, this ratio spirals out of control. Even with the most efficient propulsion systems imaginable, such as matter-antimatter annihilation, which offers 100% mass-to-energy conversion theoretically, the sheer quantity of fuel required to accelerate, decelerate, and then potentially re-accelerate a multi-generational starship would be equivalent to many times the mass of the spacecraft itself. This exponential requirement quickly leads to a scenario where the fuel needed would outweigh entire planets, creating an unmanageable engineering paradox. To go faster, you need more fuel, but more fuel means more mass, which in turn requires even more fuel in an infinite self-defeating loop. The most advanced theoretical designs for fusion or antimatter drives still show these fundamental limits, making interstellar journeys to even nearby stars a centuries-long ordeal, and intergalactic travel an absolute non-starter. Optimistic futurists and science fiction writers often propose loopholes to circumvent Einstein's speed limit, most famously the Alcubierre warp drive or traversable wormholes. The Alcubierre drive, first proposed by physicist Miguel Alcubierre in 1994, suggests a mechanism to distort spacetime itself, contracting space in front of the spacecraft and expanding it behind, thereby allowing the vessel to travel at apparent faster-than-light speeds without locally violating the speed limit within its own warped bubble. While mathematically consistent with Einstein's field equations, every analysis reveals a critical, seemingly insurmountable requirement: the need for exotic matter with negative energy density. This hypothetical substance would possess properties alien to anything we currently understand or have observed in the universe. While tiny, transient negative energy densities have been theoretically linked to phenomena like the Casimir effect, scaling this to create a stable, traversable warp bubble for a spacecraft would require quantities of exotic matter equivalent to the mass of entire planets or stars. Even refined calculations by Dr. Harold White at NASA's Eagle Works laboratory, aiming to reduce the energy requirements, still envision a need for vast amounts of exotic matter, an ingredient that remains purely speculative and may not even exist in any practical form. Similarly, wormholes, theoretical shortcuts through space-time, are also mathematically permissible solutions to Einstein's equations, extensively explored by physicists such as Kip Thorne. These cosmic tunnels could, in principle, connect distant points in space and time, offering instantaneous travel. However, like warp drives, keeping a wormhole open and stable, preventing its instantaneous collapse, would necessitate the same elusive exotic matter with negative energy density. The creation and manipulation of such a phenomenon, if it were even possible, would require energy scales and technological prowess indistinguishable from magic, far beyond any conceivable human capability. Both warp drives and wormholes, while captivating to the imagination, ultimately remain firmly in the realm of theoretical physics, facing fundamental barriers that appear just as absolute as the light speed limit itself. They do not offer a practical escape from our cosmic prison, but rather illuminate the profound depths of its design. In essence, the cosmic speed limit isn't a challenge to be overcome with more powerful engines or clever engineering. It is an intrinsic property of the universe that fundamentally defines the boundaries of travel for anything with mass. It ensures that the immense distances between celestial bodies, and especially between star systems and galaxies, translate directly into immense, often insurmountable temporal barriers. We are not just physically trapped by distance, but also by time itself, tethered to our local cosmic neighbourhood by the unyielding laws of relativistic physics. This unbreakable seal, confirmed by a century of scientific observation and experimentation, is perhaps the most absolute reason why the solar system, and indeed the Milky Way, will remain our eternal home and our inescapable prison. Having established the unyielding boundaries of distance and the absolute cosmic speed limit, we now turn to another insidious aspect of our confinement, the very nature of the space between the stars and galaxies. This is not just a void of empty distance. It is a starved, desolate realm, an environment so profoundly devoid of resources that it renders any long-duration journey an exercise in self-defeating futility. The sheer emptiness of interstellar and intergalactic space is, in itself, a wall of our cosmic prison, sealing us in through a brutal ecology of nothingness. When we imagine empty space, our terrestrial minds often conjure images of a clean, breathable vacuum, perhaps with a few scattered dust motes. The reality is far more extreme. Even within our solar system, the space between planets is not a perfect vacuum, but a very thin plasma of solar wind particles, dust, and magnetic fields. However, once we venture beyond the heliopause, the boundary where the sun's influence dramatically wanes, and truly enter interstellar space, the density plummets to levels almost incomprehensible. Here, the average density drops to a mere 1 hydrogen atom per cubic centimetre. To truly appreciate this scale shift, consider the air you breathe. It contains approximately 10^19, 10 quintillion molecules per cubic centimetre. Interstellar space is 10 quintillion times emptier than the air at sea level on Earth. It is a vacuum so profound that terrestrial laboratories struggle to replicate it for even brief periods. But even this staggering emptiness is a bustling metropolis compared to the true, ultimate void of intergalactic space. Between galaxies, the average density of matter can plunge to less than 1 atom per cubic metre. That is 1 trillion times less dense than interstellar space, and an almost inconceivable 1022 times emptier than Earth's atmosphere. This isn't just sparsely populated, it's a cosmic desert, a vast cold ocean of near absolute nothingness, stretching for millions, even billions, of light years in every direction. The Cosmic Web Imager and various studies of the intergalactic medium, utilizing observations of quasar light absorption, have meticulously confirmed this extreme dearth of matter. While there are traces of highly diffuse hot gas and dark matter filaments connecting galaxies, these structures are so tenuous that for any practical purpose of travel, they might as well not exist. This profound vacuum presents an insurmountable practical problem for any interstellar or intergalactic spacecraft: the complete absence of resources. Spacecraft, whether robotic probes or human-carrying arcs, are closed systems. They require fuel for propulsion, water and oxygen for life support, and raw materials for repair and maintenance. In the vast, starved void between stars and galaxies, there is literally nothing to harvest. No hydrogen clouds dense enough for a ramjet to scoop effectively, no asteroids to mine for metals or water ice, no atmospheres to skim for gases. Every single atom of fuel, every drop of water, every spare part, every nutrient for the crew must be carried from the point of origin. This implies that any vessel embarking on a journey of millions of years would need to be entirely self-sufficient. A completely closed ecological and industrial system, capable of sustaining itself without external input for durations that span geological epochs. Consider the immense challenges inherent in such a design. Our most ambitious attempts at creating closed-loop life support systems on Earth, such as Biosphere 2 in Arizona, have met with mixed results, often failing spectacularly within years. Oxygen levels fluctuated wildly, unforeseen chemical reactions occurred, and delicate ecological balances proved impossible to maintain. The European Space Agency's Melissa project, a decades-long endeavour to develop bioregenerative life support for long-duration space missions, has made significant progress but still faces fundamental hurdles in achieving perfect recycling and long-term stability. These systems operate under controlled conditions with the full might of Earth's technological infrastructure to support them. Now imagine such a system operating flawlessly, without human intervention for resupply or complex repairs, for millions of years, subjected to the relentless degradation of space. The very concept strains credulity. The logistical implications are staggering. If a spacecraft needs to carry all its fuel for acceleration and deceleration, all its life support consumables, and all the raw materials for potential repairs over millions of years, its initial mass would become astronomically large. This massive bulk then requires exponentially more fuel to accelerate, leading to the self-defeating spiral described earlier. The engineering challenges shift from simply building a fast ship to building an eternal, perfectly self-sustaining, self-repairing, self-reproducing mini-planet that also happens to be a spaceship. This is a qualitative leap in complexity that may be fundamentally impossible due to the laws of thermodynamics. Even if we could hypothetically design a generation ship that could somehow sustain a human population for thousands or tens of thousands of years, the issue of raw materials remains. No machine is immortal. Components degrade, break, and wear out. Over millions of years, every part of the spacecraft, from its engines to its life support systems, its hull to its internal electronics, would eventually fail. Without a readily available source of raw elements in the interstellar or intergalactic void, the ship would literally run out of materials for repair. Advanced 3D printing or self-replicating robotic factories offer some theoretical promise, but these systems themselves require feedstock, energy, and are subject to their own degradation and failure rates. They cannot conjure matter from nothing. The very concept of recycling implies some inevitable loss, some entropy that converts usable resources into unusable waste heat or chemically inert forms. Over millions of years, these tiny losses accumulate, eventually exhausting the finite material budget of any isolated vessel. Furthermore, the sheer isolation enforced by this starved void has profound implications beyond the technical. Imagine being adrift in an ocean of perfect blackness, where the nearest star is an immeasurable distance away, and the concept of refueling station is an alien fantasy. There are no friendly ports of call, no potential trade partners, no passing civilizations to offer aid or exchange knowledge. A journey through intergalactic space would be an experience of absolute, unmitigated solitude, a profound cosmic loneliness that dwarfs any terrestrial isolation. This lack of external interaction removes any possibility of unexpected breakthroughs, new resources, or external assistance that could rescue a failing mission. The ship and its inhabitants are utterly alone against the vast, empty, indifferent cosmos. The consequence of this starved void is clear. It amplifies every other barrier to interstellar and intergalactic travel. The immense distances become even more daunting when every gram of payload must be accounted for over millions of years. The energy requirements are magnified because not only must you accelerate the ship, but also all the fuel, water, air, and repair materials it will ever need. The threat of radiation becomes more critical because there's no way to replenish damaged cells or repair degraded shielding materials. and the psychological burden of such a journey is compounded by the knowledge that there is absolutely no possibility of turning back, no emergency stop, no chance of assistance from an external world. The emptiness of space is not just a vacuum, it is a vacuum of hope. A profound ecological barrier that ensures the solar system remains a permanent, inescapable home. Beyond the raw challenge of distance and the fundamental speed limit, another silent, invisible killer lurks in the cosmic void: radiation. Our planet, for all its geological turmoil and atmospheric whims, provides a sanctuary, a benevolent shield against the universe's most brutal assault. Earth's thick atmosphere and powerful magnetic field, the magnetosphere, deflect and absorb the constant barrage of high-energy particles that would otherwise sterilize our world. Venturing beyond this protective bubble, however, exposes any biological entity, and indeed any unshielded technology, to a relentless, deadly torrent of cosmic rays. This silent scythe of radiation poses perhaps the most immediate and intractable threat to any long-duration space mission, effectively forming another impregnable wall of our cosmic prison. Cosmic radiation comes in two primary forms: solar energetic particles, SEPs, and galactic cosmic rays, GCRs. SEPs are bursts of high-energy protons and electrons ejected from the Sun during solar flares and coronal mass ejections. While dangerous, these events are somewhat predictable, and spacecraft within our solar system can often take shelter or reorient themselves. Astronauts on the International Space Station, ISS, while exposed to doses 50 to 100 times higher than on Earth's surface, due to being above most of the atmosphere, are still largely protected by the Earth's magnetosphere and can retreat to shielded areas during significant solar events. Missions to Mars or the Moon will face greater challenges, but even these are relatively brief for robotic probes, or for human missions of months, not millennia. The true existential threat, however, comes from galactic cosmic rays, GCRs. These are far more energetic and insidious. GCRs are atomic nuclei, primarily protons, but also heavier elements like iron, stripped of their electrons and accelerated to nearly the speed of light by cataclysmic astrophysical events, such as supernovae explosions and active galactic nuclei across the Milky Way and beyond. Unlike SEPs, GCRs are omnipresent, streaming from all directions and largely unaffected by solar flares. Their high energy means they're extremely penetrating, capable of slicing through inches of aluminum or even water, ionizing atoms and molecules as they go. Imagine a tiny subatomic bullet traveling at nearly light speed, ripping through your cells, shredding DNA and causing irreversible damage. Now imagine millions of these bullets, every second for years, decades or millennia. The biological effects of prolonged GCR exposure are terrifying. On a cellular level, GCRs cause DNA double-strand breaks, genetic mutations, and cellular senescence. For astronauts on multi-year missions to Mars, NASA's Human Research Program estimates a significant increase in cancer risk, as well as potential for damage to the central nervous system, leading to cognitive impairment, memory loss, and even Alzheimer's-like symptoms. Vision problems, cardiovascular disease, and immunological deficiencies are also major concerns. These effects accrue over time, meaning that for a journey lasting millions of years, the radiation dose would be simply lethal. Current estimates suggest that even with advanced shielding, a biological crew exposed to intergalactic GCR levels for more than a few years would receive a cumulative dose far exceeding permissible limits, leading to inevitable death from cancer or organ failure long before reaching any distant star. The Oh My God particle, detected in 1991, provides a chilling example of the extreme energies involved. This single cosmic ray particle, a proton, possessed kinetic energy equivalent to a baseball travelling at 60 miles per hour. While extremely rare, such ultra-high energy cosmic rays demonstrate the sheer destructive power awaiting any unprotected traveller in deep space. Even if a spacecraft could somehow shield against the vast majority of GCRs, these outlier particles would inevitably penetrate, causing localized, catastrophic damage to both biological systems and sensitive electronics. Shielding against GCRs is an immense, perhaps insurmountable engineering challenge. Traditional lead or metal shielding, effective against lower energy radiation, becomes less efficient against GCRs. Instead, light, hydrogen-rich materials like polyethylene or water are considered more effective, as they can break up the heavy GCR nuclei into lighter, less damaging secondary particles. However, this spallation process itself creates a secondary radiation shower, meaning that shielding too thickly can sometimes be counterproductive, converting one form of deadly radiation into another. Furthermore, the sheer mass required for effective shielding against millions of years of GCR exposure would be astronomical. To provide a level of protection comparable to Earth's magnetosphere and atmosphere for a multi-generational starship would necessitate a vessel so massive that accelerating it to any significant fraction of light speed would be utterly impossible, returning us to Einstein's unbreakable seal. Even hypothetical active shielding technologies, which propose using powerful magnetic fields to deflect charged GCRs, face incredible obstacles. Generating a magnetic field strong and large enough to protect an entire starship would require immense power, drawing on resources that are already impossibly scarce in interstellar space. Maintaining such a field for millions of years without failure, while simultaneously enduring the ship's own degradation, adds layers of complexity that far exceed current or foreseeable engineering capabilities. The Alpha Magnetic Spectrometer, AMS-02, on the ISS has provided invaluable data on the composition and flux of cosmic rays within Earth's magnetosphere, confirming their continuous presence and complexity. Its observations underscore the sheer scale of the radiation problem in truly unprotected space, where galactic magnetic fields offer no local refuge. Beyond the biological crew, radiation also poses a catastrophic threat to the spacecraft's systems. Electronics are highly susceptible to single-event upsets, SEUs, and total ionizing dose, TID damage from cosmic rays. A single energetic particle can flip a bit in a computer's memory, leading to errors or cause a permanent latch-up, destroying a component. Over millions of years, even radiation-hardened electronics would accumulate so much damage that systems would inevitably fail. Imagine attempting to maintain a complex self-sustaining ecosystem and propulsion system when its core computational and control units are under constant silent assault, slowly being corrupted and destroyed. Redundancy can help, but eventually all redundant systems will succumb. The problem is further compounded by the nature of intergalactic space itself. While interstellar space within our galaxy offers some degree of protection from the most distant GCRs due to our galaxy's own magnetic fields, intergalactic space provides no such buffer. A spacecraft venturing between galaxies would be plunged into an even more hostile radiation environment, exposed to an unmitigated torrent of GCRs from all corners of the universe. This means that if interstellar travel is a radiation nightmare, intergalactic travel is an absolute radiation apocalypse, ensuring that any biological crew would be reduced to a cancerous ruin and any advanced electronics to inert silicon long before reaching their destination. This relentless, pervasive threat of cosmic radiation underscores the reality that space is fundamentally hostile to human life and technology over deep time. Earth's protective embrace is not merely convenient, it is an absolute prerequisite for our existence. To leave this sanctuary for millions of years, to cross the lethal zones between stars and galaxies, is to sign a death warrant for any biological crew and condemn any mechanical vessel to a slow, inevitable demise. The silent scythe of cosmic radiation is a wall around our solar system, unbreachable by flesh and blood, and barely by the toughest steel. Even if humanity could somehow overcome the mind-bending distances, bypass the cosmic speed limit, and survive the relentless assault of radiation, another fundamental law of the universe would assert its dominance, the second law of thermodynamics. This law dictates that in any isolated system, entropy, a measure of disorder or randomness, always tends to increase over time. What this means for a spacecraft is devastatingly simple. The ship, like all things, will slowly, inevitably degrade and die. This principle of the ship's slow death is not a design flaw to be engineered around. It is an inherent unyielding property of existence that ensures our cosmic prison walls will stand eternal. No machine runs forever. This is a truth we observe in every aspect of our daily lives. From our cars to our computers, components wear out, materials fatigue, connections corrode, and systems fail. On Earth, We combat this through constant maintenance, repair, and replacement, drawing on a vast industrial infrastructure and an abundant supply of raw materials. But a spacecraft on an interstellar or intergalactic voyage is, by definition, an isolated system. It carries a finite amount of everything, and over the immense timescales involved, entropy will relentlessly take its toll. Consider the Voyager probes, humanity's most enduring deep space emissaries. Launched in 1977, these remarkable craft have operated for over 46 years, far exceeding their initial design life. Yet, even they are now succumbing to the inevitable. Their plutonium thermoelectric generators, the power source for their instruments, are slowly but inexorably depleting. Instruments have been successively shut down to conserve dwindling power. Thrusters clog, and communication systems strain to send their faint whispers across billions of miles. By 2025, it is projected that we'll lose contact with Voyager 1 forever. These are simple, robotic probes, designed for robustness, operating for mere decades. Imagine the fate of a vastly more complex, life-sustaining vessel, intended to operate for millions of years. Material science offers us stark limits. Even the most advanced alloys and composites are subject to metal fatigue, microscopic cracks that grow over time under stress. The constant vibration of engines, the differential heating and cooling cycles from solar exposure and deep space cold, and the subtle impacts of micrometeoroids, however rare, will all contribute to structural degradation. The hull of a starship, for instance, would be under continuous, though minute, bombardment from stray dust particles and high-energy cosmic rays, leading to cumulative erosion and damage. Over millions of years, these minor imperfections would compound, eventually compromising structural integrity and leading to catastrophic failure. The International Space Station, orbiting within Earth's protective magnetosphere and atmosphere, requires constant maintenance and resupply. Its solar panels degrade, its seals leak, its electronics fail, and its external surfaces are pitted by micrometeoroids. NASA estimates the ISS can only last perhaps 30 years in total. Scaling this up by a factor of hundreds of thousands for an intergalactic journey is not just a bigger engineering problem, it's a conceptual impossibility with known materials. Beyond the physical degradation of components, the very environment within a closed system decays. A multi-generational starship would need a perfectly balanced, self-sustaining ecosystem to provide food, water, and breathable air for its inhabitants. But as we learned from experiments like Biosphere 2, and even the carefully managed systems on the ISS, maintaining perfect recycling and stability is incredibly difficult. Unexpected chemical reactions can occur, altering atmospheric composition. Microbial populations can shift, leading to imbalances, crop failures, or the proliferation of pathogens. Nutrients get locked away in unusable forms. Waste products accumulate. The second law of thermodynamics guarantees that some energy will always be lost as waste heat, and some matter will always transform into less useful, more disordered states. Over millions of years, these small losses, these tiny increases in entropy, would inevitably lead to the collapse of the artificial ecosystem, leaving the crew without life support. Perfect recycling, in a truly isolated system over such timescales, may be a physical impossibility. Power generation for such a journey poses another insurmountable problem. Nuclear fission reactors require fuel rods that deplete over time, producing radioactive waste that must be safely contained for millions of years. Fusion reactors, if we ever perfect them, would still require supplies of deuterium and tritium, which are finite and cannot be easily replenished in the cosmic void. Solar panels are useless in the darkness between galaxies, where stellar light is attenuated to near invisibility. Exotic theoretical power sources, such as harvesting energy from black holes or extracting dark energy, remain purely speculative, with no known pathway to practical implementation. Any power source will eventually run down, and without power, all life support, propulsion, and communication systems on the ship would cease to function. Even the most advanced computational and quantum technologies would face degradation. Quantum decoherence, the interaction of quantum systems with their environment, would inevitably degrade quantum information over long periods, potentially rendering any quantum computers or communication systems unreliable or useless. Classical electronics would suffer from accumulated radiation damage, material fatigue, and general wear and tear. Imagine relying on a computer system that has been running continuously for millions of years, exposed to cosmic rays and microvibrations, without the possibility of software updates or hardware refreshes. The integrity of data, the reliability of navigation, and the functionality of automation would all steadily decline. The implications for a multi-generational crew are stark. They would be born, live, and die on a ship that is slowly but surely falling apart around them. Each generation would inherit a vessel in a slightly worse state than the last, with more systems failing, more resources depleted, and more repairs needed with dwindling materials. The engineering knowledge required to maintain such a complex system would need to be perfectly transmitted across thousands of generations, a formidable challenge in itself, subject to cultural drift and loss. Eventually, the ship would simply cease to be habitable, becoming a tomb drifting through the cosmic void, a testament to entropy's ultimate victory. In essence, the second law of thermodynamics acts as a universal expiration date on any self-contained long-duration system. It ensures that the very act of existing and operating causes an irreversible descent into disorder. For a journey that demands millions of years of flawless operation, the universe's fundamental tendency towards chaos guarantees that the spacecraft will ultimately become a derelict, its mission a forgotten dream. The slow death of the ship is an inescapable fate, a testament to the universe's ultimate indifference, firmly cementing the solar system as our inevitable, long-term home. Even if we could conquer the physics of distance, speed, radiation, and entropy, the most fragile element of any interstellar endeavor would be the human mind itself. We are creatures of gravity, sunlight, vast open spaces, and rich social interaction. To confine generations of humanity within a metal shell, hurtling through an eternal starless void for millions of years, would impose a psychological burden of unprecedented scale, leading to the fraying mind and the inevitable collapse of purpose and sanity. This psychological wall is perhaps the most subtle, yet ultimately most devastating barrier in our cosmic prison. Our understanding of long-duration isolation comes from terrestrial analogues: Arctic and Antarctic research stations, submarine crews, and even solitary confinement experiments. These environments, though extreme, are temporary, offer regular communication with the outside world, and hold the promise of eventual return. Yet, even under these relatively benevolent conditions, psychological challenges are pervasive. Studies of Antarctic winter overcrews, for example, frequently report symptoms of seasonal affective disorder, sleep disturbances, irritability, and interpersonal conflicts. The feeling of being cut off from the rest of humanity, even for a few months, is deeply unsettling. The Mars 500 experiment, conducted by Russia, Europe, and China, saw 6 volunteers sealed in a simulated spacecraft for 520 days, the approximate duration of a round trip to Mars. While hailed as a success, the psychological toll was undeniable. Crew members experienced sleep disorders, depression, and significant interpersonal friction. One participant became so withdrawn that he effectively ceased participating in group activities. This was just 520 days, with the full knowledge that Earth was a mere radio signal away, and an exit was always an option. Now project that isolation across millions of years, across dozens or hundreds of human generations, with no hope of ever seeing Earth again, no real-time communication, and no possibility of rescue. The psychological pressures would be amplified to an unimaginable degree. A key element of human well-being is a sense of purpose and hope. For a generation ship, the purpose of the initial crew would be clear: to launch humanity to a new home. But what about the 100th generation, the 1,000th, or the 10,000th generation? These individuals would be born into a tin can, knowing only the sterile confines of their vessel and the endless blackness outside. Their great-great-great-grandchildren times 1,000 would still be light years from any destination. How do you instill a sense of meaningful purpose when the goal is so impossibly distant, so abstract, and so utterly disconnected from the lived experience of any individual? The sheer temporal scale of the journey would create a profound existential crisis for every generation, leading to a loss of meaning that could unravel the very fabric of their society. The lack of environmental variety is another critical factor. Humans evolved in a world of immense sensory stimulation, changing seasons, diverse landscapes, varied weather, and an endless array of sights, sounds, and smells. A spacecraft, no matter how large, would be an inherently monotonous environment. Even if designed with vast internal biomes, these would be finite and unchanging, eventually leading to sensory deprivation and profound boredom. Studies of long-duration submariners show that even within relatively diverse, though confined, environments, the lack of natural light cycles and external stimuli leads to cognitive decline and mood disorders. Over millions of years, the psychological impact of such unchanging confinement would be devastating, potentially leading to widespread anomie, apathy, or even mass psychosis. Social cohesion would also be incredibly fragile. Humanity is not a monolithic entity. We are prone to conflict, tribalism, and social stratification. Confined within a finite space with finite resources, the potential for internal strife would be enormous. Disputes over power, resources, or ideology, which on Earth can be diffused by emigration or expansion, would have no outlet. A small, isolated population, forced to live in close quarters for thousands of generations, would be a tinderbox of simmering tensions, genetic drift and cultural divergence, or, discussed in later sections, would further fracture the crew's identity, potentially leading to schisms, civil wars, and the ultimate destruction of the mission from within. The psychological fragility of the human collective, as much as the individual, would be tested to its breaking point. Consider the societal structures necessary to maintain such a mission. How would leadership be chosen? How would laws be enforced? How would education and scientific knowledge be preserved and transmitted accurately over millions of years without the cultural context of a home planet or external interaction? These are not minor logistical issues, but fundamental challenges to the very concept of a coherent, functional society. Errors in transmission, deliberate manipulation, or accidental loss of knowledge could lead to a cultural dark age, rendering the crew unable to understand or even maintain their own technology. The generation gap we experience on Earth over mere decades would become a chasm spanning entire epochs on a starship, rendering each new generation culturally alien to its predecessors. The very concept of home would be distorted. For generations born and raised on the ship, the vessel itself would be their entire universe. Yet, it would also be a prison, a vehicle hurtling towards an abstract, distant promise. The psychological attachment to such a precarious, transient existence, without the deep evolutionary resonance of a stable planetary home, is unknown. Would they maintain a connection to Earth, a world their ancestors left millions of years ago, a world they have only seen in digital records? Or would they develop an entirely new identity, one that views the destination, if it is ever reached, as an alien invasion rather than a homecoming? This identity crisis, played out across centuries, could lead to a complete breakdown of any original mission parameters. Moreover, the human body is inextricably linked to the mind. The chronic stress of isolation, the lack of natural light, the absence of gravity or the presence of artificial gravity, and the constrained diet would all have cascading effects on mental health. Neurotransmitters would be imbalanced, sleep cycles disrupted, and the very architecture of the brain could change over generations. We're only beginning to understand the intricate interplay between environment, physiology, and psychology from studies like Scott Kelly's Year in Space, which showed profound changes in gene expression and cognitive function. Projecting these changes over millions of years suggests a biological and psychological transformation that could render the future inhabitants of the ship unrecognizable as human, or simply lead to mental degradation and extinction. In summary, the journey to another star, let alone another galaxy, is not merely a technological problem. It is a profound existential crucible for the human spirit. The relentless monotony, the crushing isolation, the unimaginable temporal scales, and the inevitable social fragmentation would combine to erode purpose, induce despair, and ultimately lead to the psychological collapse of the crew. The human mind, adapted over millions of years to a vibrant, diverse, and socially complex planetary environment, is simply not engineered for the eternal, unchanging, and profoundly lonely void of interstellar travel. This psychological wall is perhaps the most absolute barrier, ensuring that even if we could build the perfect ship, the people within it would likely cease to be human or cease to function long before reaching their elusive destination. The dream of interstellar travel often glosses over a fundamental and relentless challenge: how to keep humans alive, fed, and breathing for millions of years in the profound isolation of deep space. This isn't just a matter of stashing enough provisions, it demands a perfectly closed system, a miniature Earth where everything is recycled and nothing is lost. Yet, as our terrestrial experiments and orbital outposts have repeatedly demonstrated, closed systems are inherently open problems, fragile, prone to failure, and ultimately unable to overcome the universe's most unforgiving laws over cosmic timescales. Earth itself is the ultimate closed ecological system, a planetary-scale marvel of interconnected biospheres where everything from water to carbon is meticulously recycled. Humanity, however, operates within this larger system, constantly drawing resources and expelling waste. To replicate this intricate balance within the finite confines of a spacecraft is a task of immense, perhaps impossible, complexity. The challenge lies in creating a perfectly self-sustaining environment that can not only maintain its equilibrium for millennia, but also adapt to unforeseen changes without external input. Our most ambitious attempt to create a completely sealed, self-sustaining human habitat on Earth was Biosphere 2, an enormous facility built in Arizona in the early 1990s. 7 scientists sealed themselves inside for 2 years with the goal of demonstrating the viability of closed ecological systems for space colonization. The experiment, while yielding invaluable data, ultimately highlighted the immense fragility of such systems. Oxygen levels mysteriously plummeted, carbon dioxide spiked, crops failed, and various insect and microbial populations either died off or exploded in uncontrolled fashion. The carefully designed ecosystem began to collapse, forcing external intervention to maintain the crew's survival. Biosphere 2, a multi-million-dollar project on Earth with immediate access to expertise and resources, failed to maintain perfect self-sufficiency for a mere 2 years. Scaling this up for a million-year journey through a hostile vacuum seems an act of pure fantasy. The International Space Station, ISS, offers another crucial lesson. Despite its advanced technology and the constant efforts of international teams of scientists, the ISS is far from a closed system. It requires continuous resupply missions from Earth, bringing fresh food, water, air, and, critically, replacement parts and components. While the ISS does incorporate sophisticated recycling systems for water and air, achieving efficiencies in the high 90 percentiles, it still loses an unavoidable fraction to waste heat, unrecoverable compounds, and system inefficiencies. For a crew of 6, the ISS still requires roughly 15,000 pounds of supplies per year. Extrapolate that for a journey of a million years, and even a 99% recycling efficiency still translates into carrying an impossible amount of residual waste, and requiring an equally impossible amount of replacement parts for systems that will inevitably fail. The second law of thermodynamics, our old nemesis, is once again at play here. It states that entropy always increases in isolated systems. In practical terms, this means perfect recycling is thermodynamically impossible. Every process, every energy conversion, every biological cycle will inevitably generate some unusable waste heat or transform some usable resource into a less useful form. Over millions of years, these minute losses accumulate into an existential threat. The ship's internal environment will gradually degrade, its resources dwindle, and its delicate balance will tip irrevocably towards disorder. Beyond the macroscopic issues, the microscopic world presents its own set of open problems. A sealed environment is a petri dish for microbial evolution. The bacteria, fungi, and viruses that coexist with humans and are vital to a healthy ecosystem would themselves be evolving in an accelerated fashion due to the unique pressures of a closed artificial environment. Experiments conducted on the ISS, for instance, have shown that bacteria like E. coli can develop thicker cell walls and increased antibiotic resistance in microgravity. Over millions of years, the essential gut microbiome of the human crew could evolve into something unrecognizable, potentially becoming pathogenic or simply incompatible with human physiology, leading to widespread illness and death. New, unexpected chemical reactions could occur between materials, outgassing toxins or corroding vital components in ways impossible to predict from Earth. Furthermore, the very concept of supplies becomes an issue. Even if perfect recycling could somehow be achieved for consumables like food and water, what about the raw materials needed for maintenance and repair? Every repair job, every replacement part requires raw elements. A starship would need to carry not only its initial operational mass, but also a vast reserve of every conceivable raw material, metals, ceramics, polymers, rare earth elements, to sustain repairs for millions of years. This would make the ship impossibly massive, and again, we face the intractable problem of accelerating such a behemoth to meaningful speeds. Harvesting these materials from the near-perfect vacuum of intergalactic space is, as discussed, an impossibility. The biological evolution of the human crew itself adds another layer of complexity to the closed ecosystem problem. Over millions of years, the human body would adapt to the unique conditions of the ship: altered gravity, constrained diet, specific lighting, peculiar microbial environment. These adaptations could lead to profound changes in metabolism, immune function, and physiological needs. What started as a perfectly balanced ecosystem for Homo sapiens might become utterly unsuitable for their descendants, who have evolved into a distinct species with different requirements. The very success of the system in maintaining life might, paradoxically, lead to its undoing by creating inhabitants for whom the original parameters are no longer viable. In essence, a generation ship is not just a vessel. It is a forced experiment in long-term, multi-generational closed-system ecology. Every data point from our current limited experience points to the extreme fragility and ultimate unsustainability of such systems over the immense timescales required for interstellar, let alone intergalactic travel. The closed system is a theoretical ideal that, in practice, always leaks, degrades, and ultimately fails. This inherent fragility, this inability to achieve true eternal self-sufficiency, ensures that our cosmic prison walls are not just physical, but biological and ecological as well, binding us forever to the singular, self-renewing bounty of our home planet. So far, we've explored the direct barriers to leaving our solar system, the mind-bending distances, the absolute speed limit, the starved vacuum, the lethal radiation, and the inevitable degradation of matter and mind. But there is another, even more profound cosmic force actively working against our escape. A force that literally stretches the universe itself, pushing galaxies away from each other at ever-increasing speeds. This is the insidious work of dark energy, the driver of the expanding chasm, and it presents an insurmountable barrier to intergalactic travel, ensuring our permanent isolation within our own local group of galaxies. The discovery of dark energy is one of the most significant astrophysical findings of the past few decades, earning the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees. Before the late 1980s, cosmologists generally believed that the universe's expansion, initiated by the Big Bang, would either slow down due to the gravitational pull of all matter, or perhaps even reverse into a big crunch. However, observations of Type-Year supernovae by the Supernova Cosmology Project and the High-Z Supernova Search Team revealed something astonishing and entirely unexpected. Distant supernovae appeared fainter than they should, implying that the universe's expansion was not slowing down, but actually accelerating. This acceleration required a new, mysterious component to the universe's energy density, something that acts as a repulsive force, pushing space-time apart. We call this enigmatic force dark energy. According to the Lambda CDM model, our current standard model of cosmology, dark energy makes up approximately 68% of the universe's total mass energy content. In contrast, ordinary matter, everything we can see and touch, including stars, planets, and ourselves, accounts for only about 5%. Dark matter, another invisible component, makes up roughly 27%. It is this overwhelming dominance of dark energy that dictates the universe's ultimate fate and sets the final, unbreachable wall of our cosmic prison. To understand the practical implications for space travel, we must grasp the concept of the Hubble constant, which describes the rate at which the universe is expanding. Currently, this rate is approximately 70 kilometers per second per megaparsec. What this means is that for every 3.26 million light-years of distance between 2 points in space, the space between them is expanding an additional 70 kilometers per second. This isn't galaxies moving through space, it's space itself, stretching, carrying the galaxies along for the ride. While our nearest large neighbour, Andromeda, is actually moving towards us due to local gravitational attraction, destined to collide with the Milky Way in 4.5 billion years, virtually every other major galaxy is receding, and the farther away a galaxy is, the faster it recedes, because there's simply more space between us and it to expand. The terrifying part is that this expansion is accelerating. The Dark Energy Survey, using the Blanco telescope in Chile, has meticulously mapped millions of galaxies to trace this acceleration, confirming its unequivocal reality. Dark energy is winning the cosmic tug-of-war against gravity, ensuring that the chasm between cosmic islands grows wider, faster, with every passing moment. What this means for intergalactic travel is catastrophic. Galaxies that are currently at a distance of about 16 billion light-years are already receding from us at speeds greater than the speed of light. This is a critical distinction. These galaxies are not violating Einstein's special relativity because they are not moving through space faster than light. Rather, the space between us and them is expanding faster than light. We can still see them because we are observing light. They emitted billions of years ago when they were closer and receding at slower speeds, but any light they emit now will never reach us. They have crossed what is known as the cosmic event horizon. This cosmic event horizon functions exactly like a black hole's event horizon, but in reverse. Once a galaxy crosses this boundary, it becomes causally disconnected from us. No matter how fast we travel, no matter how powerful our engines, we can never reach it, and its future light will never reach us. It's lost to us forever. The Sloan Digital Sky surveys comprehensive 3D maps of the universe's large-scale structure by observing galaxies at various distances and thus various epochs, provide a direct historical record of this accelerating expansion. The data consistently shows that this acceleration began about 5 billion years ago and has been increasing ever since. Future projections based on these observations are stark. The Planck satellite's detailed map of the cosmic microwave background, the afterglow of the Big Bang, precisely measures the universe's composition, confirming the 68% dominance of dark energy. This dominance is not static. The relative density of dark energy is increasing as the universe expands, meaning its repulsive effect will only grow stronger. In approximately 100 billion years, all galaxies outside our local group, the Milky Way, Andromeda, Triangulum, and a few dozen smaller dwarf galaxies, will have receded beyond our cosmic event horizon. They will be utterly invisible, lost to us forever in an ocean of expanding darkness. At that point, the local group itself will have merged into one enormous elliptical galaxy, sometimes dubbed Milkomeda. This gargantuan galaxy will float alone in the vast cosmic void, an isolated island of light surrounded by an infinite, impenetrable darkness. Any future civilization arising within Milkomeda would look out into a night sky completely devoid of other galaxies. They would have no way of knowing about the Big Bang, the accelerating expansion, or the existence of other galaxies beyond their own, for all evidence would have been stretched and redshifted out of detectability. The universe would appear to them as an isolated, finite island. The illustrious simulation, one of the most sophisticated computer models of cosmic evolution, visually demonstrates this future isolation. It shows how the intricate cosmic web of galactic filaments and clusters, visible today, will gradually be torn apart by dark energy. Clusters will disconnect, then galaxies within clusters will drift apart, until only gravitationally bound groups like ours remain. This is not science fiction. It is the inevitable consequence of measured physics, confirmed by instruments like the Baryon Oscillation Spectroscopic Survey, BOSS, which traces the characteristic scale imprinted by sound waves in the early universe, allowing us to precisely measure expansion history. The European Space Agency's Euclid mission, launched in 2023, is specifically designed to further refine our understanding of dark energy and cosmic acceleration. While its billions of galaxy observations will provide unprecedented detail, every refinement to date has only reinforced this basic, chilling picture. The universe is actively pulling itself apart, and there is nothing we can do to stop it. The expanding chasm ensures that intergalactic travel is not just difficult, but fundamentally impossible, making our solar system and its galaxy our eternal, inescapable home. The universe is not just vast, it is actively, relentlessly isolating us, as if the physical barriers of distance, speed, radiation, entropy, and cosmic expansion weren't enough. We must now confront a more profound existential question that sharpens the edges of our cosmic prison. Are we truly alone? The baffling silence from the vast expanse of the cosmos, despite the sheer number of potentially habitable worlds, points to a sobering possibility known as the Fermi paradox. This paradox, the puzzling absence of obvious alien civilizations, suggests that a great filter might be at play, a hurdle so immense that it prevents intelligent spacefaring life from becoming common. If this filter lies ahead of us, it means our dreams of interstellar colonization, already constrained by physics, might be universally self-defeating. If it lies behind us, it means our isolation is simply a reflection of an extraordinary cosmic rarity. Either way, it profoundly impacts our dreams of escape. The Drake equation, formulated by astronomer Frank Drake in 1961, was an early attempt to estimate the number of communicative civilizations in our galaxy. It multiplies several probabilities: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction of planets where life arises, the fraction where intelligent life evolves, the fraction that develop technology, and the length of time such civilizations release detectable signals. Early estimates, even conservative ones, often yielded millions of potential civilizations within the Milky Way. Yet, after more than 60 years of dedicated searching by projects like SETI, the silence remains deafening. No unambiguous radio signals, no optical laser communications, no signs of colossal megastructures like Dyson spheres, no self-replicating probes. Nothing. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of planetary abundance. Its data revealed that planets are not rare but common. Statistical analyses suggest that nearly every star hosts at least one planet. Crucially, Kepler confirmed thousands of exoplanets and indicated that Earth-sized planets within the habitable zones of their stars, where liquid water could exist, are not rare either. There could be tens of billions, perhaps even 100 billion, potentially habitable worlds in our galaxy alone. The Transiting Exoplanet Survey satellite, TESS, has continued this census, discovering planets around nearby, bright stars. The James Webb Space Telescope, JWST, is now peering into the atmospheres of some of these exoplanets, searching for biosignatures, combinations of gases like oxygen and methane that might indicate the presence of life. So far, every world examined appears sterile, a cosmic tableau of natural chemistry, devoid of life's telltale breath or technology's industrial haze. If intelligent, technological civilizations are indeed common, then by now at least one of them should have spread across the galaxy. Even at a modest fraction of light speed, a civilization could colonize the entire Milky Way in a few million years, a cosmic blink compared to the galaxy's 13 billion year age. This colonization could occur through slow generational starships, or more efficiently, through self-replicating probes, designed to travel to new systems, establish a base, replicate themselves, and then send out more probes. Yet, we observe no evidence of such galactic empires, no pan-galactic engineering projects, no signs of widespread technological activity. This profound absence is the core of the Fermi paradox, and it forces us to consider several disturbing possibilities, each reinforcing the sense of our unique and likely permanent cosmic isolation. One possibility is that life itself, the jump from non-living chemistry to the first self-replicating cell, is extraordinarily rare. Despite decades of intense research, laboratory experiments have successfully produced amino acids and other fundamental building blocks of life from primordial conditions, but never actual, replicating life. The precise conditions, the exact sequence of events, and the improbable chemical pathways required for a biogenesis might be so vanishingly specific that Earth is one of the very few places, perhaps the only place, where it has ever occurred. We might truly be cosmic lottery winners, clinging to life on an improbable oasis in a vast, sterile universe. The rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee, argues that a confluence of extremely improbable astrophysical and geological events is necessary for complex multicellular life, let alone intelligence. This includes a stable star, a rocky planet in the habitable zone, a large moon to stabilize axial tilt, Jupiter-sized planets to clear away asteroids, plate tectonics to regulate climate, and a strong magnetic field to deflect radiation, each a statistical longshot that significantly reduces the probability of Earth-like worlds. Another filter might be the evolution of intelligence. Even if simple life is common, the development of complex multicellularity, and then self-awareness, technology, and the desire to explore could be an incredibly unlikely step. Earth's history supports this. For 3 billion years, life remained microscopic. Complex, multicellular life only arose about 600 million years ago. Intelligence capable of technology has existed for a cosmic microsecond. The evolution of mitochondria, a one-time event where one cell engulfed another in a symbiotic relationship, provided the energy revolution necessary for complex life. This unique event suggests that the path to intelligence is fraught with highly improbable evolutionary bottlenecks. Perhaps the most chilling possibility, and one that directly impacts our ability to leave the solar system, is that the great filter lies ahead of us. This implies that civilizations, upon reaching a certain level of technological prowess, inevitably destroy themselves. Nuclear war, runaway climate change, uncontrolled artificial intelligence, bioengineered plagues, or unforeseen existential risks inherent in advanced technology might be the universal doom of all intelligent species. The doomsday clock, maintained by the Bulletin of the Atomic Scientists, perpetually reminds us of humanity's precarious position, often just minutes to midnight. If this is the case, then any civilization that reaches a stage capable of interstellar travel simply doesn't survive long enough to achieve it, thereby explaining the cosmic silence. The harsh realities of long-duration space travel, radiation, resource scarcity, psychological breakdown, could themselves be part of this filter, demonstrating that the universe simply doesn't permit such ventures without irreversible self-destruction. The zoo hypothesis, or planetarium hypothesis, offer alternative solutions, suggesting aliens are hiding from us, observing us, or perhaps we are living in a simulation. While intriguing, these don't change our fundamental predicament. If they are hiding, they are not helping us leave, nor are we likely to stumble upon them during an interstellar journey. We remain isolated, whether alone or merely quarantined. Recent discoveries only sharpen the paradox. Oumuamua, the first confirmed interstellar object to pass through our solar system in 2017, proved that objects do travel between stars. Its unusual shape and trajectory sparked brief speculation about its artificial origin, though it was ultimately deemed natural. The subsequent detection of Borisov, another interstellar comet, further confirmed this. If natural rocks can make the journey, why haven't we seen any artificial probes? This reinforces the notion of extreme rarity for advanced life. The search for extraterrestrial intelligence continues to expand, from traditional radio SETI to optical SETI, looking for laser communications, and ambitious projects like Breakthrough Starshot, which proposes sending tiny light-sail probes to Proxima Centauri. These efforts, while demonstrating our enduring curiosity, simultaneously underscore our cosmic isolation. We are shouting into a profound void that offers no discernible answer, reinforcing the terrifying possibility that our solar system is not just a physical prison, but an existential island in a universe teeming with beautiful yet silent galaxies. If we are alone, or nearly so, then the dream of reaching other potentially habitable worlds for companionship, cultural exchange, or even just evidence of life becomes tragically pointless. Our cosmic prison walls are not only physical and temporal, but potentially existential, sealing us into a profound and permanent solitude. Even if humanity could conquer the physical and biological barriers of deep space, the immense distances, the speed limit, the radiation, the entropy, and the fragility of our own ecosystems and minds, we would face a final, perhaps most insidious, barrier, the complete breakdown of coherent civilization. Communication is the very glue that holds societies together, fostering shared culture, governance, and scientific progress. Yet, the immutable light-speed barrier ensures that any interstellar or intergalactic expansion would inevitably fragment humanity into isolated islands, each evolving independently, until they no longer recognize each other as kin, leading to the Great Unraveling. Consider the communication delays within our own relatively tiny solar system. A simple radio message to Mars, depending on orbital positions, can take anywhere from 4 to 24 minutes to arrive. For the New Horizons probe venturing beyond Pluto, signals require over 4.5 hours for one-way travel. Our most distant emissaries, the Voyager probes, now in interstellar space, take over 22 hours for a signal to reach Earth. These delays are already significant enough to necessitate sophisticated protocols like DTN, delay-tolerant networking, for robotic missions, where real-time interaction is impossible. The sheer temporal lag creates operational challenges that fundamentally alter how we interact with our own machines, let alone other human settlements. Now, extrapolate these delays to the scale of light years. To Proxima Centauri b, our nearest potentially habitable neighbour, a message would take over 4 years to arrive, and a round-trip conversation would span more than 8 years. Imagine trying to resolve a political crisis, coordinate a scientific endeavour, or even simply share a cultural story across such a gulf. The feedback loops that define any functioning society, governmental decrees, economic transactions, educational curricula, artistic movements, would stretch into multi-year, then multi-century, and finally multi-millennial absurdities. To Andromeda, our closest major galaxy, a message would take 2.5 million years to reach its destination, and a response would not arrive for 5 million years. In that incomprehensible span, the genus Homo might well rise and fall multiple times. Any message sent would be received by beings as genetically and culturally distinct from the senders as we are from our earliest hominid ancestors. The bandwidth problem compounds the delay. Interstellar and intergalactic communication faces the brutal physics of the inverse square law. Signal strength diminishes rapidly with distance. Humanity's most powerful deliberate broadcast, the Arecibo message, would be undetectable with our current technology at distances of just a few hundred light-years. Across millions of light-years, maintaining any meaningful communication channel would require impossibly powerful transmitters or impossibly vast receivers, technologies that border on the fantastical. Information theory, pioneered by Claude Shannon, sets fundamental limits on communication, defining a channel's finite capacity based on its bandwidth and signal-to-noise ratio. Cosmic distances ensure that noise from cosmic rays, interstellar medium, and quantum uncertainty would overwhelm any signals, requiring extensive error correction that further reduces already minimal data rates. Even the sophisticated antennas of NASA's Deep Space Network struggle to maintain a few bits per second, with probes merely light hours away. Scaling this to intergalactic distances might yield only bits per year, or even per century, rendering communication practically non-existent. This profound informational isolation would shatter any hope of a unified human civilization. Earth governments already struggle to coordinate across time zones. The Roman Empire, for all its might, ultimately collapsed partly due to communication delays across mere thousands of kilometers. An intergalactic civilization would face delays millions of times longer. Central authority would become impossible. Each colony, each generation ship, each newly settled world would inevitably develop independent governance, divergent goals, and unique value systems. Without constant real-time feedback, distinct political and legal traditions would emerge, rendering concepts of intergalactic law or unified policy meaningless. Cultural and linguistic drift would accelerate this fragmentation. Human languages change dramatically over millennia. Old English from just 1,000 years ago is largely unintelligible to modern speakers. Linear B, used 3,000 years ago, required decades to decipher. Messages crossing millions of years would be utterly alien, even if sent by descendants of Earth humans. Art, literature, music, and philosophy would diverge into mutually incomprehensible forms. There would be no shared cultural narrative, no common heritage to bind these disparate outposts of humanity. Each would develop its own myths, its own history, its own understanding of who and what it is, disconnected from any overarching human story. Technological divergence would be equally profound. Each isolated world or starship would confront unique environmental challenges and possess different available resources. Necessity, combined with random discoveries, would push technological development in divergent directions. After millions of years, the technologies developed by one colony might be mutually incomprehensible to another. Imagine trying to explain the internet or quantum computing to ancient Romans, then multiply that gap by thousands. There would be no shared technological base, no ability to collaborate on grand projects, and no possibility of exchanging scientific or engineering breakthroughs in real time. The light cone problem highlights the most fundamental aspect of this disconnection. In space-time, each event has a past light cone, the events that could have influenced it, and a future light cone, the events it could influence. Locations separated by millions of light years have barely overlapping light cones. They literally exist in different causal universes, unable to share experiences, coordinate actions, or even fundamentally influence each other beyond the most ancient, long-dead signals. This isn't just a communication delay. It's a breakdown of causality itself between distant parts of a supposed civilization. Some might propose quantum entanglement as a solution, a way to communicate instantaneously across vast distances. However, this is a common misconception. While entangled particles exhibit instantaneous correlation, the no communication theorem is a fundamental principle of quantum mechanics. No information can be transmitted through entanglement alone. Every proposed quantum communication scheme, if it respects known physics, ultimately reduces to classical communication, limited by the speed of light. Entanglement offers no escape from our cosmic prison's communication walls. Even artificial intelligence, often seen as a panacea for long-duration missions, would face the same limitations. Immortal AI could maintain continuity across million-year journeys, but without real-time communication, AI systems evolving independently on different worlds would diverge just as dramatically as biological intelligence. They might develop distinct cognitive architectures, problem-solving methods, and even forms of consciousness that become mutually incomprehensible or even hostile. The very concept of synchronized global time would also break down due to relativity, making any joint action impossible when different worlds cannot even agree on when now is. In the end, the light-speed barrier ensures that humanity, if it were ever to spread beyond the solar system, would not create a unified empire but a constellation of isolated, self-contained, and ultimately alien civilizations. Each would be a lost echo of Earth, culturally, linguistically, and technologically distinct, strangers to each other across vast gulfs of space and time. The Great Unraveling would transform any initial humanity into a myriad of unrelated species, each trapped in its own cosmic island, knowing nothing of the others. Our prison, then, is not just physical, but also informational and societal, ensuring that our destiny is one of permanent, profound fragmentation. Beyond the confines of our home, we have journeyed through the cosmic barriers, unearthing the profound, unyielding truths that bind us to our celestial birthplace. We confronted the mind-bending chasm of light years that stretches to even our nearest stellar neighbours, a gulf that renders any conventional journey a multi-millennial, multi-generational odyssey. We grappled with Einstein's unbreakable seal, the cosmic speed limit of light, which transforms any ambition of relativistic travel for massive objects into an infinite energy paradox, confirmed by the merciless physics of particle accelerators. We peered into the starved void of interstellar and intergalactic space, an environment so profoundly empty it offers no fuel, no resources, no possibility of resupply, condemning any long-duration vessel to an inevitable slow death by starvation and entropy. The relentless, silent scythe of cosmic radiation emerged as another existential threat, a pervasive deluge of high-energy particles that would shred human biology and degrade spacecraft electronics over any meaningful timescale, turning deep space into a lethal crucible beyond any conceivable shielding. We then faced the inevitable degradation of matter itself, governed by the second law of thermodynamics, dictating that no machine, no closed ecosystem, no structure can defy entropy for millions of years, leading to the ship's slow, mechanical and biological demise. The psychological collapse of the crew, the fraying of the human mind under the weight of eternal isolation, and the loss of purpose across countless generations, revealed itself as perhaps the most insidious yet absolute barrier to our expansion. Then, we ascended to the grandest scale of all, confronting the expanding chasm of dark energy, a mysterious force actively pulling the universe apart, pushing distant galaxies beyond a cosmic event horizon from which their light and any hope of our reaching them is forever lost. Finally, we contemplated the chilling implications of the Fermi paradox and the Great Filter, pondering whether our cosmic isolation is a symptom of life's extraordinary rarity, intelligence's precariousness, or a universal self-destructive fate that prevents any civilization from enduring long enough to escape its home system. Each barrier, in isolation, is immense. Together, they form an unbreachable wall, a cosmic prison constructed by the fundamental laws of existence. This isn't a temporary technological challenge, it's the permanent architecture of reality. But here, at the culmination of this daunting intellectual journey, we must pivot, for in confronting the stark, unyielding reality of our cosmic confinement, a profound truth emerges. Our prison is, in fact, a paradise. Our isolation, far from being a tragedy, is what imbues our existence with unparalleled preciousness and grants our endeavours a profound, focused meaning. The universe has not trapped us in a barren cell, but embraced us within an empire of stars, vast beyond our current comprehension, yet coherent enough to be our ultimate inheritance. Consider for a moment the sheer, breathtaking scale of what we do possess. The Milky Way, our galactic home, contains an estimated 400 billion stars. To put this in perspective, if humanity were to visit a new star system every single second, it would take over 12,000 years just to see them all. At a more realistic pace, exploring one new system per year, it would take 400 billion years, a span more than 30 times the current age of the universe, to merely visit every star within our own galaxy. This is not a limitation. This is an abundance that defies imagination, an endless frontier waiting within our grasp. Recent astronomical discoveries continually unveil the true richness of this galactic inheritance. Missions like the Kepler Space Telescope and TESS have revolutionized our understanding of exoplanets, demonstrating that planets are not the exception, but the rule. Statistical analyses suggest our galaxy alone harbors over 100 billion planets, with tens of billions potentially residing in the habitable zones of their stars. Each of these worlds is a unique crucible of geology, atmosphere, and perhaps biology. We've found hot Jupiters orbiting their stars in mere days, super-Earths with surfaces of diamond or water, rogue planets drifting in eternal darkness, and systems like TRAPPIST-1 with 7 Earth-sized worlds packed tightly around a single star. The diversity and sheer number of these celestial bodies within our single galaxy far surpass anything science fiction has ever placed across entire fictional universes. Our confinement within the Milky Way is not a dearth of destinations, but an embarrassment of riches, offering an inexhaustible supply of mysteries to unravel, phenomena to study, and potentially worlds to explore and even transform. This understanding of our limits liberates us. Instead of pursuing impossible, fantastical dreams of intergalactic empire, we are grounded in a profound, achievable reality: interstellar travel. While monumentally difficult and requiring timescales that challenge our current biological and technological paradigms, is not fundamentally impossible within our own galaxy. Concepts like generation ships, long-duration suspended animation, or radical life extension, while still nascent, are avenues of scientific and engineering inquiry that hold actual theoretical pathways to success. We can realistically dream of humanity spreading across our galaxy over millions of years, a future where our descendants populate countless stars, not as conquerors of the cosmos, but as stewards of this magnificent bounded realm. Our cosmic isolation, as highlighted by the Fermi paradox, amplifies our significance. If life is rare, and intelligence rarer still, then Earth might indeed harbour the only conscious observers in the Milky Way. We are not merely one civilization among an infinite sea of others. We might be the sole witnesses to our galaxy's breathtaking beauty, the only minds capable of comprehending its vastness and complexity. Every sunrise, every scientific breakthrough, every moment of awe inspired by the night sky might be a unique phenomenon in our cosmic neighbourhood. This uniqueness bestows upon us an extraordinary responsibility. We are not just living for ourselves, but as the representatives of what is possible in this galaxy. If we succumb to self-destruction through conflict, environmental collapse, or technological hubris, we might be extinguishing the only consciousness the Milky Way has ever produced, turning our vibrant galactic island into an empty monument to a fleeting, self-annihilating awareness. Our survival, therefore, transcends mere self-interest. It becomes a cosmic imperative. The finite scope of our galaxy, rather than limiting us, makes true understanding a conceivable goal. Unlike an infinite universe, our Milky Way is, in principle, comprehensible. Future humanity could realistically catalogue every star, map every planet, and understand every phenomenon within its 400 billion stars. We could, over eons, achieve a complete scientific and experiential knowledge of our cosmic home, an intellectual conquest that would be impossible if we were scattered across an infinite sea of galaxies. This focused ambition allows for concentrated effort, leading to deeper, more profound discoveries than any scattered, impossible intergalactic exploration could ever hope to yield. Instruments like the James Webb Space Telescope and the upcoming extremely large telescopes are already demonstrating the power of deeply examining our galactic neighbourhood, unveiling secrets far beyond our initial expectations. Perhaps, too, being trapped together might ultimately save us from ourselves. If intergalactic escape were easy, humanity might fragment irreversibly, our disparate colonies diverging into alien species, lost to each other forever, but confined to one galaxy. We are forced to eventually reconcile, cooperate, and unite. Our shared imprisonment, our common destiny within these spiral arms, might be the ultimate catalyst that finally brings humanity together as a single species with a singular, shared purpose. Even the anticipated collision with Andromeda in 5 billion years rather than a catastrophe becomes a future opportunity, a majestic galactic merger that will double our cosmic real estate, triggering new star formation and creating fresh worlds for our descendants to explore, expanding our prison into an even grander domain. Understanding our limits paradoxically liberates us from impossible expectations. We are not failing to build an intergalactic civilization. We are succeeding at what is genuinely possible. Every probe we send to another star, every world we terraform within our system, every nascent colony we establish, is a monumental victory against the immense distances and harsh physics that define our reality. Our galactic isolation makes every discovery within our Milky Way infinitely more precious. Should we find life on Europa or Enceladus, decode signals from another civilization within our galaxy, or uncover new physics, these will not be routine events in a galaxy-spanning empire, but unique, invaluable moments in our singular, isolated pocket of consciousness. Scarcity in this context creates immeasurable value, rendering every galactic discovery priceless. The artistic and cultural implications are equally profound. Confined to one galaxy, human culture will retain enough coherence to share art, literature, music, and ideas across vast but not infinite distances. The works we create, the stories we tell, the knowledge we accumulate will not be lost to impossible voids, but can enrich all of humanity across our galactic realm. Our limitation teaches humility and fosters wisdom. The universe has shown us our place, not as potential gods ruling countless galaxies, but as conscious matter confined to one magnificent galactic island. This humility, this acceptance of our natural bounds, might be the very wisdom we need to survive and thrive. The search for meaning, too, becomes clearer and more potent when bounded. Instead of pursuing an elusive purpose in impossible infinite expansion, we find it in perfecting our corner of the universe. We can transform the Milky Way into a garden of consciousness, a beacon of life and intelligence in an otherwise empty cosmos. Future technologies, fusion power, antimatter production, life extension, terraforming, advanced artificial intelligence, can be directed towards the achievable, the vital task of making our galaxy a true home for humanity and whatever intelligences we create or encounter. Our cosmic story, instead of fragmenting across incoherent distances, remains unified, a complete tale with a beginning, a middle, and an ever-unfolding end, making it meaningful rather than diluted into infinite meaninglessness. So, when you next gaze up at the night sky, don't see a prison of unreachable lights. See your inheritance. See 400 billion stars that belong to you and your descendants. Every point of light in the Milky Way is a destination you, or your children's children, might someday reach. That is not limitation. That is abundance beyond imagination. We will never leave the Milky Way, but that is not a tragedy. It is a gift. It means we are home. It means we belong here. It means this galaxy, vast and beautiful beyond comprehension, is ours to explore, to understand, and to cherish. We are not trapped. We are embraced by the spiral arms of stars that define the boundaries of our cosmic kingdom. The universe has given us precisely what we need. Not infinite, diluting space, but a bounded realm, vast enough for endless discovery, yet coherent enough to remain our true home. The Milky Way is our cradle and our destiny, our prison and our paradise, our limitation and our liberation. Embrace our galactic confinement. Celebrate that we have 400 billion stars to explore, rather than mourning the trillions we will never reach. Find joy in the fact that we are all in this together, one species in one galaxy, sharing one cosmic destiny. The universe has given us the Milky Way, and that is more than enough for any species to find meaning, purpose, and endless wonder. We will never leave the Milky Way, and perhaps, in the end, that is exactly as it should be.